Hi, and welcome to this lesson. Today we're going to be talking about continuity of functions. I'm splitting this video up into two parts, just so that it's not too long. Continuity can be thought of in this way: that a small change in x produces a very small change in y. That is mathematically. In physical phenomenon, most physical things are continuous in nature. If you think of the growth of a child, like their height growth in height or their weight gain, that is a continuous function. It doesn't skip all of a sudden to be a kid's not 2 feet one day and then he's 8 feet the next day or 6 feet the next day. There's a continuous pattern of growth. Or like temperature change, when we go from cool in the morning to hot in the afternoon, back to cool in the night, that's a continuous function. Graphically speaking, continuity can be thought of as this way. If you were going to draw a function, if you put your pencil down and you don't lift it until you get to the end of the function, then that's a continuous function. If you have to lift up your pencil to move it to a different spot to draw it again, then that is discontinuous. You had to move a spot. So that is how you can think about continuity. The definition of continuity is this: a function f is continuous at a number a if the limit as x goes to a of the function is equal to what that function is defined at that value a. That implies basically three things. The first thing that this definition implies is that the function f is defined at a. F is defined at a, or basically that a is in the domain of f. This little symbol here means is a member of the domain. The second thing that this implies is that the limit exists. The limit as x goes to a of f of x exists. And then the third thing that this implies is that the limit, not only does it exist, but that the limit as x goes to a of f of x is equal to where it's defined at a. It implies these three things. So just so we can really get an understanding of this definition and how it relates, I'm going to draw a graph. And then on your worksheet, example 1, at which numbers is f discontinuous and why, we'll say where it's discontinuous, and then we'll say, give the reason why it doesn't meet this definition. So right here is a function we're going to draw, and here's my x-axis and here's my y-axis. And I'm going to say that right here this is 1, 2, 3, 4, 5. Let's just see. Let's have it be open circle here at 1 somewhere. And then it goes down to, here's 3. It's going to go down here. It's going to go up here, maybe. And then at 3, it's maybe open circle here. And then it goes around to 5 where it's open circle. And then it continues, and at 5, it is defined right there. Okay, so let's say, where did we have to lift our pencil if we were drawing this? And so we could say this function is discontinuous at, this is example 1 on your sheet. Okay, it's discontinuous at x equals to 1. It's got an open circle there. We had to lift our pencil and move. To 3, this is 3. 4, okay, it's discontinuous at 3, at x is 3, and it's discontinuous at 5. There's an open circle, and there's where it's defined to be, so it's discontinuous at x equals to 5. Now, y, okay, a y, in other words, does it not meet this definition? So, at x equals to 1, is it defined at 1? What is f of 1? It is undefined at 1. So for that reason, see, it doesn't meet number 1. We could just say that the function f of 1 is undefined. That is why it didn't meet that definition. At x equals to 3. Well, can we try that again? Is it defined at f of 3? It is defined at f of 3. You see that closed circle? It is defined at f of 3. But does the limit exist at f of 3? Let's see. If we tried to find the limit as it approaches 3 from the left, it would be down here. From the right, it would be up here. So these one-sided limits are not agreeing. For this, we could use this. We could say, number 2, the limit as x goes to 3, the limit as x approaches 3 of f of x does not exist. We could say that about that one. What about number 5? Is it defined at 5? Let's see. Yes, it is. We have this closed circle there. Does the limit exist at 5? As we approach it from the left and as we approach it from the right, yes, it does exist. But the limit as x goes to 5 is this number up here. Maybe we'll call that 6. We'll say, and the limit in f of 5, f of 5 is equal to up here, maybe this is 6, and the limit as x goes to 5 is going to be this open circle right here. That's what it looks like it's getting close to. So for number 5, we could say, well, the limit as x approaches 5 of this function does not equal to where it's defined to be at 5. So if you can, when you're asked to say where's discontinuous and why, or why is this not continuous, you could use any one of these that fits the bill for that. Okay, next on your sheet, I have us drawing 4 different functions and just talking about where it's discontinuous, and we're going to learn to name different types of discontinuity. So the first function is f of x is equal to x squared minus x minus 2 over x minus 2. This is a rational function. So let me make some more room on my board. It is defined to be a polynomial divided by another polynomial. And so we're familiar with that. These have things like asymptotes, vertical asymptotes, horizontal asymptotes, holes, sometimes oblique asymptotes. That's what rational functions have. But for this particular one, I gave us the function f of x is x squared minus x minus 2. This is example 2, and this is A. F of x is x squared minus x minus 2 over x minus 2. Okay, so this is a rational function. Sometimes when you're given rational functions, you should think about what is the domain, and can I factor anything to see if there's any holes. And if you can factor it and there is a cancellation, there's a hole, but also you're allowed to work with the simplified version of the function. So let's see if that can help us out. Can I factor the numerator? Let's give it a shot. Let's see. I think this will factor into x minus 2 times x plus 1. Let's see. X squared plus x minus 2 is minus x minus 2. It does factor. And we do get a cancellation. Now that never changes the domain. The domain is everything except for x can equal 2. Everything except for 2. That doesn't change the domain. But we are allowed to work with this simplified version of the function. So basically f of x is equal to x plus 1, given that x cannot equal to 2. All right. Well, f of x could also be called y. And if I write it like that, it's easy to see that this is a line. Y equals mx plus b. What is the slope of this line? The slope of this line is the number in front of the x, which is 1 over 1. And the y-intercept is this point right here, 0, 1. Let's just graph this real quick. I could go up to 0, 1. I could go up 1, right 1. I could go down 1, left 1, either way. But this is basically what this function is going to look like. However, you can never forget that it's not okay for it to equal 2. So we go over here to 1, and we'll go over here to 2, and we'll go up here to where it meets that, and we'll draw an open circle right there because it's not allowed to equal to 2. This y value right here is 3, okay? All right, so we say, oh, okay, this function, that's what it looks like. That's what this rational function looks like. Basically, this would have this meets the requirements. The power of the numerator is 1 higher than the denominator. And so this meets the requirement for an oblique asymptote. So an oblique asymptote does exist, and basically the graph is the oblique asymptote in this instance. Anyway, let's talk about discontinuity. We would say this graph, it's discontinuous at x equals to 2. Now, why? Well, we could use the reason that f of 2 is undefined. F of 2 is undefined. That would take care of it. The limit as x goes to 2 is defined. It's equal to 3, but f of 2 is undefined, so it's discontinuous. Okay, let's look at another example. What if we've got b? This is a piecewise function. F of x is equal to 1 over x squared for values of x that are not, where x is not equal to 0, which is good because if x was equal to 0, it's undefined. And it's equal to 1. It's equal to 1 if x is equal to 0, when x is equal to 0. Okay, so this 1 over x squared is a rational function. This is one of our basic functions. I'm just going to graph it for you and show you. It has a, this is what 1 over x squared looks like. It has a horizontal asymptote at y equals to 0. It has a vertical asymptote at x equals to 0. So this is what it looks like everywhere except 0. But at the one value it's undefined, they defined it for us, and they said it's defined right here. Here's the solid circle at 1 when x is 0. So this is what this graph looks like, this piecewise functions. All right, where is it discontinuous? Well, it's discontinuous at x equals to 0 because that is where I had to lift my pencil to start drawing again. So it's discontinuous at x equals to 0. That's where the problem is. Now why? We cannot use the same reason there. We cannot say that it's because f of 0 is undefined, because it sure is defined. It's defined to be 1. But we can say that the limit as x approaches 0, from the right, what is it? It's positive infinity. From the left, what is it? It's positive infinity. So the limit as x goes to 0 of f of x is infinity, right? And f of 0 is equal to 1. We can say that this does not equal to f of 0, so it's discontinuous for that reason. All right, let's look at another one. What if we've got, basically it's a, only I'm going to just see. So f of x is equal to this same function, only they said let's let it equal to 1 when x is 2. So it's this function, only let's let it equal to 1 when x is 2. So we already graphed this, so I'm going to erase some of this busyness right here. Let's just look at the graph right here. So it's equal to this if x does not equal to 2, because that's where it's undefined, right? And it's equal to 1. Is that what I put there? It's equal to 1. Oh, no, I lost my paper. Yeah, if x is equal to 2. So let's just see what that would look like. When x is equal to 2, we say we're right here at 1. But the function, this did not fill in that little hole right there. If it filled in that hole, it would be called continuous. But this is not continuous, it's discontinuous at x is equal to 2, not because the function's undefined at 2, but because the limit as x approaches 2 of f of x does not equal to f of 2, because f of 2 is 1 and the limit as x goes to f of x is 3. What could we do? Let's push this just a little bit further. How could we define this function so that it was continuous? Well, we could do that pretty easily just by changing this a little bit. We could say everywhere that the function doesn't equal to 2, it looks like this line, but at the one value when it equals to 2, let's make it equal to 3. Let's make it equal to 3. Then what would our graph look like? Well, then our graph would look like this. At 2, we'd say it's up here at 3, and so that little point would be filled in by that, and then we'd have a continuous graph. Okay, I meant to go through here and say what kinds of discontinuities are these. Okay, let's look at this one right here. This one where the graph is going up here to infinity, this is called an infinite discontinuity. An infinite discontinuity. Okay, a minute ago, when I was messing around with this, before I pushed this a little bit further, and I called this I made it continuous. This is called a removable discontinuity. So it's called a removable discontinuity because of what we just did. Because we can remove the discontinuity part of this by defining it in a certain way to make it continuous. That's why that gets that name. Okay, let's look at the last one. And the last one's what we looked at an earlier video. This is the step function. Okay, so it's a step function, but it's the greatest integer function. So let's look at D real quick. F of x is equal to the greatest integer function. And so the greatest integer function is defined to be, it equals to x if x is an integer, is a member of the integers. It's equal to the greatest integer less than x if x is not an integer. And I'm abbreviating here for time because I already defined this in an earlier video. So you are already familiar with the greatest integer function. So let's just graph it. Here is y and here is x. So the greatest integer function says if x is an integer, then it's equal to that value. So right here, at x is 0, it's equal to 0. At x is 1, it's equal to 1. At x is 2, it's equal to 2. At x is 3, it's equal to 3. Oops. At x is negative 1, it's equal to y, it's equal to y is negative 1. At negative 2, it's equal to negative 2, and so on. So if x is an integer, it equals to that value. Now, what about in between integers? Well, this part, if it's not equal to an integer, then it's equal to the greatest integer less than that. So for instance, 2.5, let's think about 2.5. 2.5 is not an integer, so it falls back to the greatest integer less than that, which would be 2. So if I'm right here at 2.5, right here, I'm falling back to 2, I'm still at 2. So I'm at 2 until I get to 3, then I hop up to 3 until I get to 4, and so on. So this is how the greatest integer function looks. I refer to it as a step function because it looks like steps. So let's talk about discontinuities. Where is this function discontinuous and where is it continuous? Well, let's look at it. It's continuous right here, right here, right here, right here, right here, right here. It's discontinuous every time we had to move, every step we take, right? It's discontinuous. What's making that, why is it discontinuous? Where is it discontinuous? It's discontinuous whenever x is equal to an integer. When x is an integer, once it hits an integer, it jumps to the next value. It jumps to that value. And so because it's jumping, this type of discontinuity is called a jump. A jump discontinuity. All right, so those are the various types of discontinuities, and that's the definition of discontinuity. And so this is part 1 of this lecture, and so we're going to finish the worksheet on the second video.